people have got a little bit tired from the subject, so the audience is definitely smaller than it was yesterday. Anyway, just I recall that our last result, which I discussed yesterday, was that there is a distinguished quantum change of variables in which these operators A of u are diagonal, and in this case the Toda equation is reduced to a system of compatible difference equations which are acting just on one variable. And here's the solution. The solution is just the product of gamma functions, in contrast to the periodic case where we get a second order equation which is much more difficult to solve. But then, of course, the question is how to pass to the coordinate representation, because we have an abstract change of variables and we want to go back to the coordinate representation. And for that, we need to construct a unitary operator which relates the representation in which of separated variables to the standard representation, the coordinate representation. And just here, the idea is very simple. If we look just the kernel, the Schwarz kernel of a unitary operator is nothing but a complete system of eigenfunctions for some auxiliary linear problem. So instead of giving you a unitary operator, I must just give you an auxiliary linear problem whose solution gives you this system of eigenfunctions which does the job. And we are just following the Dirac ideology, and we are looking for transformation operators which go from one representation to another. And just to label such representation, I shall use, I shall indicate the complete set of observables, just a commutative family of operators which are diagonal in this representation. So we have the coordinate representation in which the diagonal operators are the standard coordinates, and separation representation which diagonalizes separator roots of C, Cn. And finally the spectral representation which diagonalizes root of An. And here is the kernel observation, the key observation. Diagonalization of this operator C is equivalent to the solution of rank n-1 Toda. This is because, well, just let me go a few slides back. Where it is. Oh, here you are. In equation 37, you see that this operator C in a view, whose roots we have been studying, is nothing but the operator An-1 multiplied by an extra variable, which this variable Qn is absent from the operator content of An-1, which contains all other variables. And so it's just a commuting operator which we add on the left. And consequently, we have this representation. So finding a diagonal representation for C amounts to solving the Toda lattice of rank n-1, where we have also have to add two extra variables, Qn and the conjugate momentum. So I get back to my transparencies. So this is my key observation. I just introduce this Dirac notation just to write in a condensed way the eigenfunctions, which are nothing but the kernels of the corresponding translation operators. And so by Dirac chain rule, we have this formula, which means that, well, just this free exponential in front of other wave functions, nothing but the wave functions associated with the extra coordinate xn which we have added. And here comes the wave function of rank n-1 Toda. And this is immediately gives you a basis for induction, because you can reconstruct psi lambda in exactly the same way as we did it on this stage. Simply we have less variables involved. And so we can iterate, and in this way we get the following very remarkable formula, which has been deduced by Lebedev and Harshov, and this is called the generalized Mellenburg formula. The classical Mellenburg formula is for functions of one variable. For SL2 case, the Toda lattice equation coincides up to some natural change of variables with the equation for Whittaker functions from classical function theory. And there is this formula which represents the Whittaker function as a Fourier transform over some quotient of gamma functions. And here we have a similar formula. It's a genuine Fourier transform, and the function which we transform is just the quotient of several gamma functions. The only important difference is that we have much more integrations than there are independent variables. So we perform recursive ordinary Fourier transform with a linear phase function, but we do much more transforms than there are variables. That's because we must make this apply this recursive procedure. So does it happen. Now this is okay. It's a brilliant formula, but it doesn't immediately bear on representation theory of SON. What we really want to do is just to deduce some message from this absolutely marvelous formula for the representation theory of principal series of SLN. And now it's not immediate, because just the Toda lattice is associated not with the full representation space of this representation, but just with a single or with a pair of vectors, special vectors such as Whittaker vector and spherical vector, and you get a radial part of the Laplacian, not the Laplacian itself. And so it's not obvious that you can manage to deduce some direct conclusions for the entire representation space. Now this is the case. And here comes another construction again due to Lebedev and friends, and which can be regarded as a far-going generalization of two classical constructions. One due to Gelfand and Zetlin back to 1950s, and another one due to Gelfand and Kirillov. And that's a Gelfand-Kirillov conjecture, and I shall say a few words about that. Now, here comes the idea in modern setting. We want to construct some maximum abelian subalgebra in the universal enveloping algebra of SLN. For that, we consider this natural chain of subalgebras. Just each subalgebra is embedded into the previous one as an upper lower corner of the matrix. And inside each, so we have the corresponding embeddings of universal enveloping algebra, and inside each algebra there is a center. And so we have a chain of embedded centers. So the big center commutes with everything, and so it commutes with the former, with the algebra associated with n-1, and so it commutes with n-2, etc., etc. So we get an abelian subalgebra, which is called Gelfand-Tsetlin subalgebra. One can show that this is a maximum abelian subalgebra in U of GLN. And so we can look for the joint spectrum of this maximum abelian subalgebra. And it's parameterized by the spectra of individual centra. And for each center, by Harish-Chandra theorem, the center is isomorphic to the algebra of polynomials, of symmetric polynomials in several variables. So we have many variables on each level, and we get a triangular array of spectral variables which parameterize the joint spectrum. And because actually we have this Harish-Chandra theorem which said that the center is isomorphic to the algebra of symmetric polynomials. So actually these lambdas, they parameterize not the spectra of the centers themselves, but rather of their huge algebraic extensions. On each level we must pass to the algebraic extension which replaces the symmetric polynomials with all polynomials. And in this way we get a huge algebraic extension of this Gelfand-Tsetlin algebra with the Gola group, which is S1 cross S2 cross etc. cross Sn, the symmetric group. And if you just look back at this formula, the Mellenburg formula, the integration variables which enter this formula, they form precisely this kind of array. So it's not a coincidence, it's the same thing. But we are now going to interpret these integration variables as spectral variables associated with this chain of embedded centers. So we get this huge algebra, and we can add to this, it's an abelian algebra, so we can regard these lambdas as generalized momenta. And we can also introduce conjugate coordinates, which are acting as translations in this representation. And we do it for all levels except for the last one, because the eigenvalues of the Laplacians themselves, they parameterize you, they are just the modular of representations. So there are no conjugates for this on this upper level, on the level n. There are no conjugate variables because we are taking these spectral values of lambda n, capital N, as parameters of representation. These are precisely the parameters of the.
So this will be the Casimirs.
Yes, these are on the upper level. These are the Casimirs, the overall Casimirs of the big algebra.
Okay. So
and the embedded Casimirs, they are not commuting with everything, because they are commuting only with elements which belong to that particular subalgebra. So we have this very big algebra, which will play a prominent role in this construction, which is generated by all these lambdas, which form this triangular array, plus the conjugate translation operators, and this will give you a huge Weil algebra. Now, this construction reminds you of an important idea by Gelfand and Kirillov. They noticed that if you just take the universal dynamic algebra, you pass to the quotient field, and then you look what happens. And they realized that up to some details, it's always isomorphic to the standard Weil algebra. You can, in this big quotient field generated by this non-commutative universal dynamic algebra, you can always find conjugate momenta and conjugate coordinates and conjugate momenta, plus you have enough Casimirs. The Casimirs, they are just parameters. So we have an algebra which depends on several parameters, which are just the eigenvalues of the Casimirs plus the coordinates and momenta in U number. Actually, when they proved, they didn't prove it in full generality, but they did prove it for semi-simple algebras. And in so doing, they were obliged just to pass to this central extension, to this algebraic extension. So they proved it not for the universal dynamic algebra itself, but you can do it this way. You can take U of G, and then you tensor it with P of A star over PW of A star. So they pass to this algebraic extension by extending the ring of the Casimirs. The ring of the Casimirs is replaced by what they call virtual Casimirs. These are just the elements which parameterized by elements of this algebraic extension of the center. And with this precision, they have proved their theorem for all semi-simple Lie algebras. That's a 1966 paper, I guess. So here we are obliged to do the same thing. We have to pass to our spectra are parameterized by these lambdas, and they naturally, they are the spectra not of the original algebra, but of its algebraic extension. It makes no harm whatever. So we can now introduce it's a not very good definition, but it's a morally it's correct. We just consider functions, regular functions with probably meromorphic functions with singularity somewhere, which depend on all these complex variables, and then we can define a representation of this Weil algebra acting by multiplication. So there are multiplication operators, of course, and there are translation operators by some x. So this operator acts by translation by x on place G. This is what we call a Gelfand-Zetlin representation. This is not good analytically because the space of meromorphic functions of this kind is very hard to control. But never mind. And we are now going to construct a linear representation of our algebra by means of these multiplication and translation operators. So here you are. This is the definition. We must define, first we define operators which correspond to elementary matrices, just the diagonal matrices and the matrices which correspond to simple roots. So here they are. And as you see, there are multiplication operators and there are translation operators. And this I is not an index, it's just a root of -1. And theorem, which was proved by these three authors, is that these formula define you a linear representation of our universal Mellenburg algebra in the space of meromorphic functions. Now just we have to prove it by hand, just by controlling the well-known algebraic relations which exist between these operators. We must check the defining relations, and that's true. It's not difficult, although it's a little bit long, but just let me draw your attention to the fact that it is something highly non-usual, because we are dealing with a representation of universal Mellenburg algebra by difference operators, not by differential operators. Just for decades, people were studying how to integrate representations of Lie algebras given by differential operators to produce some unitary representations or just some well-defined representations in some appropriate functional sense of the Lie group. But here we are bound to an entirely new type of analytic problem, because people do not know how to control difference operators of this kind. They are unbounded because of this imaginary direction of the in which the translation operator acts. So it acts across if you just choose a contour and you look at your functions which are defined on the contour and then extend it analytically to some vicinity of that contour, then this translation operator acts across the contour, and this makes much trouble. And so the conventional theory of Lie groups and Lie algebra says nothing about such kind of representation. But it's a great challenge, because we are now see that we are obliged to work with such things, and we have to learn how to control them in some way or other. So all the disadvantages of this fancy definitions, they are immediately compensated by the following properties, which are, in fact, well, I'm just starting with stating for instance, we are going to construct Whittaker vectors in this representation. Whittaker vectors are just eigenvectors of the nilpotent subalgebra generated by positive roots or by negative roots, so you can just look for two vectors of this kind, and you can find solutions. And incidentally, just one of the Whittaker vector in this realization is just one. It's not very interesting, but the other one is of the type which is very remarkable. It's again a product of functions of one variable, and that's the key property of this Gelfand-Zetlin representation. In this representation, the Whittaker vectors are just products. This function Sn, which enters the previous formula, is just the product of gamma functions of special combinations of variables, and so we get a formula for these Whittaker vectors. This is already much more convincing than the previous formula, because now we have a representation of the entire Lie algebra this very remarkable representation in which the Whittaker vectors are products. What is still more surprising, now just let me skip a few slides and I shall return back to this. Here is another remarkable fact. We can, in the same representation, we are now writing equation for the spherical vector. And the spherical vector is just annihilated by this combination of operators corresponding to positive and negative simple roots. So this is the defining relation for spherical vector. And again, you get a simple difference equation, which is solved by this product of gamma functions. So we write this phi n in this form, and then here is the spherical vector. So in that same Gelfand-Zetlin representation, not only the Whittaker vector, but also the spherical vector is given in this very fancy way. And so I just presumed that all experts in representation theory now must abandon all their work. They must just look very thoroughly at these formulas, because there's something terribly new. Neither Gelfand nor other classics have ever seen such formula, although they are rather close to what they have invented themselves. But this represents just a sort of a breakthrough. And of course, we know rather little about this representation, but we know enough to produce. So I'm just getting back a little bit. We know enough to produce explicit formulas for spherical functions and for Whittaker functions, which are associated with this with the spherical vectors and Whittaker vectors for this in this model. Now, just let me do it. First of all, we can just this representation defined formally in the space of all meromorphic functions of unprecise type. Well, it's something terrible. It's very bad analytically, but we can look at a much smaller representation, which is just cyclically generated by the Whittaker vectors, which we have just exhibited. And this way we just get two Whittaker modules. And it's easy to see that this W is A G Z times W. This is a very simple characteristic of this cyclic submodule, just because the entire algebra is generated by shifts and translations, and because the Whittaker vector satisfies difference equations, it's only the abelian algebra AGZ which is acting freely on our Whittaker vector. So the theorem says that the Whittaker module associated with our Whittaker vector, which is a submodule in this terrible representation, is just freely generated by the Gelfand-Zetlin algebra. Just apply all elements of all embedded center to the Whittaker vector, and you will get an irreducible submodule in this very big linear space. So we have this Whittaker module, and already we know much about Whittaker modules from the classical paper of Cossens, which you can consult. So this is the statement which I wanted to explain. Moreover, there is a natural Hermitian pairing between the two dual models associated with two vertical vectors associated with two dual nilpotent subalgebras.
Excuse me, I go to the highest weight because in the pairing, submodule becomes quotient. So in this pairing that you're doing.
Well, we just, as far as I understand, it's true as stated. And this pairing is again given by some weighted integral, which we can, well, just, it's not absolutely clear, nor is it trivial, because when we do integration, we must draw a contour, which just goes in a clever way around the singularities of gamma function. So the claim, which I'm not sure that I shall prove it now, but the claim made in the paper of Gerasimov, Kharchov, and Lebedev is that you can do it unambiguously. And we again, this is not something which we have seen already. If we want to have this simple Hermitian property, we must impose conditions on the Plancherel measure, and we get a first order difference equation for the Plancherel measure, and again it can be solved. Effectively, we get the same measure which we have seen already. So far so good. And now we come up to this spherical vector. I show this formula once again, and we have this theorem. Now, what we can do about vertical functions and spherical functions? Of course, it's very difficult to integrate such representation to a full representation of the group. And that's a terrible question, which may be solvable when we get a more profound understanding of the theory of these different separators. But if we look at the restriction of this, what we want is just to compute the vertical function and the spherical functions on the Cartan subgroup. And that's simple, or relatively simple, because the Cartan subgroup in this representation acts by multiplication operators. And so it's not terribly difficult. And in this way, we get this explicit, absolutely new formula for spherical functions. So we have already seen same kind of formula for vertical functions, but in that same representation, the Gelfand-Zetlin representation, the matrix coefficient of the exponential of the Cartan element, which is well defined in this representation, is given by this formula. This is a new formula. Harishchandra didn't know it. And so again, something terribly important has happened, because Harishchandra just knew an abstract integral formula, a rather complicated one, which depended on the details of, say, Iwasawa decomposition of the group. It had just a standard asymptotic expansion for large values of our variable x. Then intervened the C function, and for the C function, by some miraculous change of variables, we knew the explicit formula with gamma functions. But now here is a much more elementary formula for the spherical function itself. It's a Fourier transform. This is a linear phase function of an aggregate of gamma functions. And the contour must be chosen in a smart way, just to avoid poles of the gamma function. It's not difficult to choose a contour. So this is a terribly new formula. I presume that now the entire Poisson theory becomes much more simple, because just to compute asymptotics of this integral, you just use Cauchy theorem. Just look at the poles, and you compute the residues, and you get, of course, you get the C function as a coefficient in your asymptotic expansion very easily. So it's a very interesting new step.
I have a question.
Yes.
But Alexandra proves the integrability of the matrix element, because once you have that, you have a representation, so you sort of get the whole thing, right? I'm a bit confused on what you're doing. You're not doing that, right?
Well, I'm just, from Harish-Chandra theory, you can draw the following consequence. The principal series, the class 1 principal series representation is completely characterized by the spherical vector. There exists just a unique representation such that, etc. So it's enough to reconstruct the entire representations once we know the spherical function or the Whittaker function. So at least implicitly, we know enough to reproduce the representation completely. What is very remarkable is that this is a much more elementary formula. It's an elementary, well, in principle, elementary Fourier transform of your So this is the question which I addressed already just orally. This is something which remains almost totally unexplored. But you see, just as usual, the analytic formula, they are more clever than we are. So once we have got such kind of formula, we must forget everything, and we must start to study the analytic background which is compatible with these formulas. This is something which hasn't been done by anybody. Of course, not by the classical authors which have done the main job. They have invented the formula, but they stopped here. They didn't discuss the background. And that's what I'm going just to invite people to do. It's very important just that not only just, you see, just so far there are two different communities which are working on the subject. There are experts in integrable systems and quantum integrable systems in particular, which know much, but generally they are not very great experts in representation theory, and they're not really interested in the internal problems of representation theory. And on the other hand, there are people in representation theory which are very much interested in representation theory, but which are totally unaware of what's going just around in the now just the question is whether we can do better. We know intertwining operators, which again are reproduced, which we are given by complicated kernels and which we have factorized representation, but can we just realize them explicitly in this Gelfand-Zetlin representation? Also, you see, just if you just you will ask, of course, and that's very much important. The high standard of Harish-Chandra just implies that we have to do everything in a classification-independent way for any semi-simple Lie algebra. Now we are rather far from that ideal Harish-Chandra situation, because we have done everything for GLN. Is it possible to do it for other classical algebras? The answer is yes, with some pain. You can produce, if you just work with Toda lattice, and you want to get the Toda lattice for other series than AN, you must look at the Toda lattice with boundary conditions. There is a special theory which accounts for that, again, mainly due to Sklanin. And in this way, you can deal with orthogonal series B and C and D. That's possible. Rather bulky. So the formula are there. The Mellenburg formula for other classical series is known, but the method is very far from general just wisdom of Harishchandra, and it doesn't apply to exceptional Lie algebras. So it's another challenge for good experts in semi-simple Lie groups and Lie algebras just to do it in a better way. Also, the Gelfand-Zetlin construction, it is known to work for GLN, and it is also known not to work for symplectic series. So there are some troubles. We have to construct this maximum abelian subalgebra in the universal enveloping algebra. Here we did it in a fairly straightforward way using the centers of the embedded subalgebras. It's not that simple for other classical algebras, and it's absolutely not simple for exceptional Lie algebras. So again, there are plenty of trouble if you are taking this idea seriously. But this is a great challenge because we know it works. And if it works for GLN, why should it not work for E8?
Things that don't get work for classical and
Yes.
don't work for exact.
Yes. Well, just it's a terrible standard imposed by Harishchandra in his classical works that everything should be made in a classification-independent way. We are very far from that, but it's a challenge. And also, if you just look at the volume 6 of Gelfand's generalized functions, you will see that many formulae which work over R and over C, they also work for other local fields. And you have nice formula for spherical functions. You have nice definition of the local C functions. You have also the definition of the beta function in this case, and again, and the beta function is rational in the local case. So we have the formulas are analytically more simple, but the interest of these local fields is that they are just building blocks to pass to the global fields, to the groups defined over a ring of atoms. And that is what makes the most romantic part of volume 6. And it's also, well, just the key point is that you have eigenfunctions of Laplacians, which are also eigenfunctions of Hecke operators, and they satisfy the same type of functional equations. The C functions are there, and the intertwining operators are there. Many formulas are simplified, and instead of elementary functions, you are dealing now with earlier products. And instead of gamma functions, you will get zeta functions. So that is terribly romantic, because whenever you see a zeta function, Riemann zeta, that means that it's something very profound. And so just my goal in this series of talks was just to draw your attention to the fact that something very much important is about to happen in representation theory. We do not know much about the generalizations. For instance, can we apply this technique in the same generality as Harishchandra did? Harishchandra wrote a terribly complicated paper on discrete series, on infinite dimensional representations associated with compact Cartan subgroup. It's not easy to construct these representations. There are some which are constructible in holomorphic sections of some bundles, and there are some which are constructible in terms of L2 cohomology associated with also with some.
You can do it easier. I write in his papers in Anna's constructs those without cohomology. With the completion technique, you can do easy.
Well, anyway, my question is whether we can, and just by Harishchandra philosophy, from these discrete series, you can then induce continuous series. Just there are continuous series which are induced from infinite dimensional representations of the parabolics. And so it's a great question whether you can generalize this technique of separation of variables to that case and to things like Eisenstein integral, which is discussed in one of Harishchandra's last papers on parallel Schrödinger theorem, etc. So there are plenty of open questions, and it is very likely that this technique has a proper generalization to that absolute general setting. And so I just once regretted that all these discoveries came too late, because if Gelfand were alive and active as he was 30 years ago and 40 years ago, he would have acted dictatorially. He would have immediately stopped everything around him, and he would give just tasks and questions to everybody, just because it's his domain. He believed, and that was correct at his time, that he understood all the complete background of representation theory. There were some mysteries, but which he put aside, and there were also some mistakes which he did, because he unduly believed in generality of certain of his assumptions. But on the whole, the picture which he created from particular examples which he discussed since early 1950s, it was just, it could be believed to be a complete picture, just the details were to be filled in. And now something terribly new happened. We have a new paradigm, a new pattern, and something which Gelfand didn't know at all. And so I'm just inviting people who are interested in representation theory and who have ever thought about Harishchandra and Gelfand and others, it's time to take it seriously. It's a great challenge, and if ever we will be able to do it, that will definitely mark a great progress in representation theory, and maybe more, because representation theory is also well, people were very much interested in Whittaker functions, and there is an entire school of deep experts in Whittaker functions in connection with problem in analytic number theory. When you are dealing with automorphic Laplacians in higher rank, you need to work with Whittaker functions. And there are quite a few deep experts which spend their life, entire life on deducing some formulas which become totally elementary once you apply the formulas which they didn't know, the formulas of the Mellenburg type. So here the result of this work of Lebedev and others is very spectacular, because people were just deep experts on Whittaker functions. They spent their lives. They published one paper in 25 years, a paper of 250 pages, just to produce some formula, which become elementary when you know more about these Whittaker functions. So that's my story. Probably I should stop now. And I'm just, I believe that people must take seriously not my talk, but the subject of my talk.
So it's very interesting, but yeah. I have the following. So you, at the beginning, the very first lecture, you described Lattice theory very syntactically, where you realize the holomorphic, in the space of holomorphic sections, I split representation.
No, not holomorphic.
No, you did, I saw it.
No, well, just let me go back, and I'll show you that you saw something which I didn't show. It's the matter of principal series representations. Principal series representations, for instance, for SO2, yes. We have different kinds of representations. There are discrete series, which is realized in the space of holomorphic sections over the upper half plane, and also there is a, you see, just for SO2, you know, there are two kinds of coadjuvant orbits.
Sure.
Yes, and there are, if you just look at orbits associated with semi-simple elements, there are hyperboloids of this type with just linear distributions which give you Lagrange distribution on your symplectic manifold, and there are these upper and lower hyperboloids which carry complex structure. Now these two types of orbits just generate something which is associated with holomorphic sections, etc. These are the discrete series, and the parameters are indeed discrete. And here you get what Gelfand calls the principal series.
So you're interested in those?
The principal series, yes.
Okay, thank you.
And you see, just this is quite natural, because if you just look at the Toda Hamiltonian, it has a continuous spectrum. And this continuous spectrum just matches precisely with the continuous parameter for this principal series representation. And so it is. If we just look at the spherical space and we want to decompose L2 in the spherical space into irreducible components, then the key property is that the existence of a k-invariant vector. There are no k-invariant vectors in this discrete series. So by Frobenius duality, these discrete series do not contribute to the decomposition of L2 over symmetric space, say. And so as a result, our Whittaker function, which was just a matrix coefficient between spherical vector and there is no contribution of discrete series, just only principal series, and you have a continuous spectrum. Yes.
So it's really different from the...
It's really different, yes.
Any other question?
And the same thing applies, just it's these two Lagrangian distributions, they produce equivalent representations, and the equivalence is realized by these intertwining operators, the horospheric automorphism of Gelfand. And here we have two representations associated with two halves of the hyperboloid, and they're not equivalent. So here this Weil group symmetry is broken. And we have no intertwining operators between these discrete series representations. So it's a different matter. But in general, when we are dealing with higher rank case, we can take a parabolic P equal to M A N, and M may have discrete series. And so we can induce representations of our big group, taking some infinite dimensional representation of this Langlands component of the parabolic times the character of A. And this gives you a relatively, just gives you a branch in the continuous spectrum of your Laplacians. And the celebrated branch-relay theorem of Harichandra says that all these representations, which are shaped with different representations of discrete series for M and with one-dimensional representations of N, of A, all these representations which are induced in this way, they are enough to decompose the L2 over G. But when we introduce this discrete series for M, well, it becomes technically very much more difficult than it is in the standard case.
Any other question? So if not, let's thank the speaker again.